have to, okay. Let's see, can I make it? There we go. And by the time, if you've been here from the beginning, a lot of this is going to be pretty familiar to you. But here's the method from the method section, a sentence from the method section of one of my recent papers. Classification was of task, face or word, using linear support vector machines, parameter at C, partitioning on the runs, leave one run out, six-fold cross-validation, with accuracy computed by averaging across the folds. And if you come from machine learning, this might surprise you a bit. You know, linear SVMs with a fixed parameter, really? I mean, this is very much the opposite of kind of some of the deep learning philosophy. It's a very simple sort of method. But if you come from psychology or the neuroscience side of things, you might also be a bit puzzled, kind of all the choices you could do, why am I partitioning on the runs? Why am I using linear SVMs? Is this just arbitrary? So, no, it's not the arbitrary choice. These are not arbitrary choices, but these are also not the only way you could possibly do this. There's a lot of valid ways. But I'm going to try to explain some of the key aspects of fMRI data sets here in the next few minutes that are relevant for doing MVPA type analyses, and hopefully letting you better judge what are reasonable choices for the future in your own analyses. Okay, so let's start at the end. Where do we want to be when our fMRI analyses are all over? Well, I think we want to be at the right answer. I'm no philosopher. I'm not going to debate whether ultimate truth, right answers, anything like that exists. But I will claim that there is kind of a right answer of a sense in science in a practical matter, but that we can't even hope to get there unless we have valid and reliable procedures. And I like this little illustration. I pulled it from Explorable, and DVB's blog has some interesting discussion of these issues recently if you're interested in these types of topic. But I think we can all agree that validity and reliability is where we're striving. So why am I talking about validity and reliability when I'm supposed to be talking about fMRI analyses and data sets? Well, because it's a big problem. As probably most of you know, there's even some sessions and stuff on this very theme here. You know, I just did that Google search the other day for neuroimaging reliability crisis, and 700,000 hits come up at the very first pass. So my argument is that the best, quote unquote, results of MVPA or any sort of fMRI analysis are not necessarily those with the highest accuracy or whatever metric we happen to be using, but the ones that have the highest validity and reliability. And I think we have the best chance of getting to that if we really understand some of the properties of the data sets that we're working with. Hence this talk. So why is this so complex in fMRI and MVPA? And this is, some of the other speakers today have touched on some of these issues, but the way I think of it is that an awful lot of the parametric statistical theory, distributions and all that, were developed for independent measurements, when you're recording one thing from a whole bunch of different units. Stuff like DICE. And people, DICE is really easy because you just, it's discrete, independent, you roll it again, it doesn't matter roll to roll, what it got, etc. We know what the possible numbers are, we can just count the points. People and fMRI data sets are not remotely like DICE in really any respect. People change their performance over time, they maybe get worse because they're getting hungry and are tired, they get learning the task and they get a lot better over time. People are not interchangeable, people tend to act more like themselves than to other people, etc. And the physics, so this is all kind of, should be extremely familiar to you if you've done any sort of psychology statistics. It's, but there's additional complexities when you're dealing with fMRI data sets on top of all of this standard human subjects and repeated measurements type of design complexities. So finally, let me talk some fMRI. So the good thing is that fMRI BOLD actually is a non-invasive proxy measure of brain activity. There's a lot of, you can get into the quibbles, but yeah, there is bold there. I'm going to be dissing I'm going to be saying a lot of problems about bold in the next few minutes, but it is good. There is information in there. The bad is that bold is not kind of nice, neat, dice-like information. It's extremely blurred over time and space. There's a lot of artifacts. As some of the other authors were saying, speakers were saying, images are not independent. Changes from bold are quite small. I'll get into this a bit more. And the ugly is that from a machine learning point of view or statistical analysis point of view, is that the data sets tend to be very ill-posed in that we generally have far, far more dimensions, voxels, vertices, whatever, than we have examples. And machine learning statistical methods generally prefer the opposite sort of data set. So I'm going to go into a little bit more detail, but also try to emphasize how there are ways to try to still get at validity and reliability despite all of this. Okay, so bold, hopefully this is like bold in 30 seconds. Blood oxygen level dependent. The name is a very big hint there that it's related to the oxygen in the blood. It's not a direct electrical or chemical sort of measurement. So there's going to be some blurring in space at the smallest scales. How small you can go is, I think, still under a little bit of debate, but you can't get to like 1 neuron with bold. I think everybody can agree on that. There is a bottom limit of how small you can go. And also blood, you get a lot of influences from anatomy because you have like blood vessels, all of that kind of stuff that affect how your bold goes, and a lot of physiology. So if we're doing fMRI, think in terms of regions, groups of cells, not individual neurons. That's the spatial scale we're talking about. And there's also some blurring in time. We presumably all know the hemodynamic response function. Here's a canonical one. The little star is representing where the event was. That could be an extremely short event, like just getting slapped, which lasts less than a second. But the hemodynamic response, the bold, is going to be blurred over a lot more time than the actual event took. So different people, different brain regions, different sorts of responses, like a visual versus a somatosensory versus emotional event, are all going to have different HRFs, but we usually ignore that. But still, we need to think that there is some temporal uncertainty in our signal. And the TR, the sampling rate, of course, also adds some temporal uncertainty. We're not getting instant measurements of the bold. So the bottom line of all of that is that fMRI, we're talking on the scale of seconds, maybe getting about a second, but not milliseconds, I would argue, if we're doing bold. Okay, bold is very weak. So this is kind of the one that if you have a very robust stimulus, like visual checkerboard, something like that, you might get 2 to 4% change. Higher order cognitive processes are generally a lot smaller than that. Are there stronger sources of bold if we're doing fMRI than thinking? Yeah, a lot stronger. And fMRI artifacts is a huge topic. I've been spending a lot of time lately thinking about it. Ask later. And there's sessions on it. But I think that it's important that you at least have a general sense of what some of these big ones are. So this is just one slice of one little teeny example. This is these images are just slices from a brain and the standard deviation. What do you see that's brightest? It's the big blood vessels, and then some of the vessels that are going over your skull. If thinking made a bigger bold than blood, you would see the gray matter bright in these images, but you never do. It's always stuff like blood vessels and stuff that are brightest. Okay, people like to breathe and sometimes even move, and that's a very bad thing if we're doing fMRI. If you think about the physics of it, a movement of even just a millimeter or less is going to, so the physics of it is, we're doing the pulse, which lines up all the water molecules, then they come out again and it's read out. It's all of this incredibly careful timing in fMRI. And if you move even a little bit, you're going to disrupt that excitation readout type of signal. And there's the bold is going to be affected by that. There's just no way around it. If you're dealing with very complex acquisition schemes, such as like multiband or simultaneous multi-slice acquisitions, you start getting smaller and smaller voxels and or smaller and smaller TRs. All of this stuff just multiplies and really gets bigger. You can do some very serious head restraint, which helps. That's the case forge where they like model each person's head and make a 3D thing to really squash them in there against the coil. And that does reduce movement quite a bit if you can get somebody to stay in there for a couple hours. But it doesn't get rid of movement entirely because you still have stuff like the pulse goes through your scalp is enough to pick up and see. If you take a real deep breath, you can see it actually go through the ventricles. The brain is soft, it's not hard. So the brain is going to be moving even if you can fix the skull completely. And there's non-movement ways to alter bold, stuff like blood respiration, caffeine, et cetera, Yeah, I'm really going, like I said, I'm really disembold here, but there's even movement just from the magnets. If you're scanning a phantom and plotting the traces from like scanner heating, stuff like that, it looks like there's movement. And I'm not even going to go into stuff like within image and within time series effects from spatial normalization, slice timing, all of that introduces all sorts of weird dependencies. So am I saying we should just give up? No. But we do need to be extremely aware that these dependencies are in the data. And our goal is to minimize their effect and their magnitude. We're not, I at least, some people think we can maybe regress all of this out. I'm not remotely that optimistic. Proof will be in the pudding, but we need to, I think everybody can agree that we need to design our analyses such that these dependencies are not going to totally bias our results. Okay, so a few practical examples. And as several of the speakers were saying earlier, cross-validation is absolutely necessary in a lot of cases, and we need them to be as independent as possible. In practice with fMRI, that usually means that we're going to cross-validate on scanner runs, scanning sessions, or people, not individual trials, certainly not independent TRs, unless we're dealing with extremely unique situations. Yeah, they're not perfectly independent, but they're more so than volumes within a run. And yeah, I make the case that you generally need to show that it's legitimate if you're going to be doing something other than cross-validate on the run, session, or people with fMRI data. Yeah, people have covered that. Cross-modal classification, just a little shout out, that's also called like cross-class classification, things like that. An example is like if you're training with a word, like when people were reading different words and then you're testing with like images or symbols. So you have an experimentally designed and planned training and testing that can actually work exceptionally well and be independent because it's different classes. So the bottom line here is if you're going to be doing an experiment for MVPA, when you're planning the experiment, plan the cross-validation as well. Keep this in mind because there's no perfect solution, but there's a lot of people have come with me with data sets and wanted to do some classification, and I have to tell them you just can't because the distribution of the tasks within the runs is just not suitable. So for example, 4 tasks runs is generally better than 2 task runs. Balancing is helpful. There's a lot of caveats and art to it. Yeah, so the bottom line is that you want to design your experiment such that however you're doing the cross-validation, if there are some dependencies left, it's not going to positively bias your results too much, get you false positives. Feature selection, this, I'll just real quick, people have touched on, a couple people have talked on this, kind of going from biggest to smallest. You can do the whole brain, region of interest based, searchlight based. And the thing to notice here is that these are all working with spatially contiguous groups of voxels, the main methods. And this is a sensible thing to do. Adjacent voxels are not independent. So we don't want to treat them as if they are. We want to be catching groups of voxels and inferring about groups. Yeah, and an aside, if you're from the mass univariate world and doing GLMs and SPMs, there's generally a lot of smoothing, a lot of cluster corrections, this kind of stuff. That's a different mathematical way to try to get at the same sorts of non-independence. And as Jessica said earlier, a priori ROIs can be very, very good if they're actually a priori. Obviously, if you do an MVPA, pick a few of the best voxels and classify with them, it's going to work great in complete nonsense. Yeah, so this also is reiterating some of what Jessica said, that if you're interpreting at the level of regions, it's reducing your degrees of freedom, which can help, and can avoid some of the spatial uncertainty. And this is kind of paralleling some of what the earlier people said. I'm perfectly not a big fan of some of the single voxel feature selection methods, like if you're picking the 50 voxels with the highest bold, because it's just not stable. If you can get stability, maybe, but very often it's a major problem. Yeah, this thing says I have 18 minutes left, which I know is not right, so I'll just try to keep on going. But with temporal compression, that's kind of a generic term for when are we going to analyze, because the HRF is way slower than the neuronal responsive. So here's our HRF again. And it's also a lot slower than the acquisition rate that's often used in fMRI. So the idea here is that those vertical lines are when the images were acquired. And it's like, if that's a face trial and we're trying to pick a volume that has the face effect, we can't do it. It's in a lot of those volumes have a little, a varying amount of signal. So how are we going to get a face exemplar? We have to do, that's kind of this idea of temporal compression. A couple of the common methods are simply to kind of eyeball an HRF, look at which volumes ought to be in the peak and average them together and use that. It can actually work better than you would think. Parameter estimate images also are a common way of doing that. That's where you're fitting a general linear model and pulling the parameters. So you're feeding it what the bold should look like and then using the parameters as opposed to an average or something like that. These are betas if you're using SPM, COPE images if you're using FSL. They're called different things, but it's the same principle. And this can work very well because you're reducing the number of examples substantially sometimes, but it can still really improve some of the validity and reliability because you're averaging out some of this volume-to-volume noise, trial-to-trial noise. Yeah, and sometimes even going very far, like to one image, like off the results of a GLM where you're going to one image per class per person can even work well. So why are linear algorithms popular? Somebody else was touching on some of this, that the short answer is that other ones don't often do all that much better. There's some references if you want to read into some of the proper comparisons. Some of the additional answers is that if I'm dealing with somebody that's new to MVPA, I pretty much always tell them to use correlation or a linear SVM because we want to avoid adding experimenter degrees of freedom. Unless you're very careful about how you're doing your nested procedures when you're optimizing algorithms, it's easy to get a lot of experimenter degrees of freedom and overfitting very fast. And that often fMRI data sets are too small to support the full set of nested procedures that you need. Not always, but often. And they tend to be a bit more robust. Yeah, and this, as Jessica said, it's not at all trivial to interpret what's going into a linear classifier, but with a nonlinear classifier, it's a lot harder. So that's, like I was saying, it's kind of pragmatic, that in practice, linear, no optimization type algorithms are often more reliable. Not always, lots of caveats, but. And then a final kind of point is with significance testing. This is different, a slightly different way of framing it perhaps, but my answer in a lot of MVPA analyses that what we're asking with significance testing is given this data set, this analysis procedure, was this result likely to have occurred by chance? And permutation methods, randomization methods are the best choice, I would argue, for valid and reliable answers because you can actually, if you're paying attention, you can design them to account for some of these dependencies, nesting in subjects, cross-validation that are in there. And with parametric testing, fMRI data sets almost never make those, the assumptions that those need. And the idea is that we're relabeling examples to form data sets where we don't have task-related information anymore, task label-related information. And then this is, as Carson was saying before the break, that we're making a null distribution of what sort of accuracies, what kind of statistic can we expect out of our data set if there isn't any task-related information. That's what that histogram is showing. What do the accuracies look like if there is no information? Because then we have something to compare against. Because we can say then, if the true accuracy is way out in the tail, that's unlikely to have occurred by chance, and we can mathematically, count how unlikely it was. Whereas if we're in the fat part of the distribution somewhere, we can't, it's not a significant, it's something that could have occurred by chance quite easily. And yes, with these permutation and randomization type methods, the inference is generally related to the current data set, but I would say that in practice, unless you're an epidemiology person or something, that's really what you care about is the current data sets. Okay, so to try to wrap this up, hopefully it's really, really obvious by now that there are lots of artifacts and dependencies in fMRI data sets. This thing of events in people runs within sessions, voxels are in brains, people move, people's hearts beat. All of this adds dependencies. Warping to spatial templates add all sorts of, if you're normalizing to MNI space, you're adding a whole lot of dependencies right there. So we need to design our analyses that are minimizing the effects of these as much as we can, and that are robust to the dependencies that are present, in the hope of still getting it valid and reliable results. And so hopefully you won't be as puzzled if you see phrases like this, but rather think of it as kind of a way of setting up relatively conservative choices with fMRI data. And that's it. There's my money and my information. So thank you.